Today we will be looking at how to use a SmartRCP system and the templates provided to control one dual active bridge converter. So just to talk all of us the same languages, this is the main schematic of a dual active bridge converter. As you can see, there is a primary bridge, secondary bridge, transformer in the middle, two different power supplies. Actually, we will be using today a couple of laboratory power supplies. And this is, let's say, the power states. And then this lower part is what we'll be using in today's webinar as the template. So we have, or the template is comprised of a ADC stage, which will be sensing the real current of the converter. Then that signal will be compared with a reference. That error will be sent to a regulator, and the output of the regulator will modify the delay of the modulator. So this modulator actually is a single phase shift. So we will be modifying the shift between the primary and secondary bridge, and then we will obtain this current across the inductor. So we will be using a SmartRCP device. We will be using several Ethernet connectors in order to send the PWM signal to the real converter. We will be using a computer for debugging, for using the user interface, etc. And we will be controlling one of the converters that are actually designed and manufactured at PSC. This rack is comprised of three different dual active bridge converters, creating a total power of 150 kilowatts. And if we look inside, we will be seeing three power modules like that. This module is a dual active bridge converter of 50 kilowatts. It is comprised of, you can see here in the image, of the magnetics, the power PCB, the DC bus capacitors, protection, etc. So we will be making use of the dual active bridge template for SmartRCP. Those templates are already done and, let's say, fully built by PSC and delivered to the user, so user can modify them, adapt to their needs, etc. This is what the user will receive in Vivado. So what do we have in here? First of all, we have the data logger, which will work also as an oscilloscope. Then we will have several IPs, which are the SmartRCP drivers. For example, the PWM's IP, the register IP, the ADC IP, digital EO IP, etc. Then we will have a couple of IPs as closely related with the user interface, which are the write register IP, this one, and the read register IP. Those two IPs are the ones that will be continuously interchanging information with the user interface. Also, we will have in here this blue box, which is all, let's say, all architecture generic stuff. For example, the processing system, resetting system, clocks, etc. And this IP in blue here is what performs the control of the dual active bridge. We will be seeing then with higher detail in a moment. The main IP for controlling the dual active bridge is this one, which have several inputs, several outputs. You can see in here, which are the transistor gain signals. All of them are outputs. We also have the delay in case we want to analyze that, or let's say perform an analysis of this parameter. As if we look at the inputs, we have the switching frequency, the dead time, the reference current that we will be using to control, as this is a current controlling, the slew rate, which is the derivative that we will be allowing to in our system to make a modification, several controller parameters, and also the facelift limitation. So this is the IP which will be performing the control in the converter. So what we'll be looking at today? We will be using a real dual active bridge converter, as we have seen, and then it will be connected to the SmartRCP. It will interchange this signal. So we will be measuring input and output voltages and input and output currents. All of them are DC values. We will be sending 8 PWM signal to the dual active bridge converter. And in the middle, in this blue region, we will have all that is contained in Vivado. So we have the AXI-IP communication that interchange information with the user interface. In the middle, it is one of the microprocessors of the Crya K26. This communication will send and write registers that will be connected to the control IP. We also have in here the analog to digital converter drivers, which will be receiving the real waveform, the real signal from the converter, and will be just feeding to the control the real current. With that, the control IP will check the error, will send that to the compensator, and then insert that to the modulator. So the output of this IP are the gating signal, which are directly exported to the converter. All these blocks inside the blue region are inside the PL side, so are performed in FPGA side. So microprocessor is just for communication management. All in red is all that is compressed in the template that in the dual active bridge template. So we provide the FPGA and the processor code, everything. In here, you can see in bytes, this is just a screenshot of the code. In here, you can see the register exchange between the FPGA and the user interface. So as we have said, this is just a communication management system. And this is the user interface that we will be using today. This is a general, so user can parameterize it. Actually, users can modify it in here. For example, the gains of the analog chains, can compensate also the offset of the analog chains, can check the status, alarms, etc. of the control, can plotter and check in real time waveforms, and can enable and disable the converter. So in this part in here, we have the main configuration toolbar in which we can, for example, connect, disconnect, enable, disable, open parameters, save parameters, open the ADC compensation window, modify the register, open the oscilloscope, etc. In here, we have the status and alarm system in which we will be logging all the status and alarms of the converter, just to know in which scenario we are, in which part of the state machine. Then we have several regions in which we can just plot all the waveforms that we are sensing. So in this case, for example, we are checking the delay of the two bridges, the input and output voltages, and input and output current. And in here, also in the oscilloscope, we can see those waveforms with a more detailed view. So let's go with the live demonstration. So to do that, I will open Vivado. And this is just the template that we have just covered in the slices. As you can see, we have the data logger IP with all the input signal that we can connect. we have only connected these signals, but we have a lot of more signals spare that we can also connect. These blocks are just drivers for a SmartRCP system, so they make it easier to interact with the inputs and output of those systems. For example, this one is for the digital outputs. This one is just an auxiliary block for calculator MMS and average value. This is the IP for the analog to digital converters, etc. Those two IPs are the ones that will be managing the communication of and also the register exchange between the user interface and the IP and the controlling IP. As you can see, all the user register that we will be configuring in the user interface are sent to the dual active bridge controlling system, which is this block. In here, we have just, let's say, generic architecture, processing system, reset, clocks, etc. And in here, we have all the emulating stuff. We have a couple of axis blocks in order to interchange several magnitude and parameters with the IP. Those are the one connected, you see, with the controlling IP. This is the controlling IP. So this is the very same that we look in the slices. And in here, we also have a real-time emulator. This one will not be covered today, but it is provided so that you can see the possibilities of the system. So this is all Vivado. I will not open by this because the code is just quite straightforward. I will go directly to the user interface, which is this one. You can see it here, first of all, that all the measurement seems to be quite noisy. However, that is an scaling factor. As you can see in this example, the measurement is not noisy. It's just that the span we are plotting is quite tight. In here, we have already connected the real dual active bridge converter. So as you can see here, we are generating, we are moving power. So we are enabled. So in here, we can just open the register just by clicking in register. In here, we have all the register that we are interchanging with the control IP. In here, we have a lot of possibilities. For example, this one is for controlling in open or closed loop. This one is the switching frequency, the times, parameters, values, etc. Those are the phase-it limits. And in here, we have the reference current. This is the current that we will use as a reference for our control. Remember that we are controlling the dual active bridge in current. Also, we can, for example, modify the ADC just by clicking in here in ADC, change. We can change the name, the limit, the waiting time. Waiting time is related with the alarms. So, for example, if an input of in an analog channel is bigger than a certain threshold for this time, it will trigger the alarm. Also, we can filter the signal, we can include an offset again, etc. I will open in here the oscilloscope. The oscilloscope. In here, we can select between all the different signal that we will be including. So I will choose input and output current and input and output voltages. Voltages are in the lower side and current in the upper side. So as you can see in here, we have an input and an output voltage of 500 volts. So our dual active bridge is just, let's say, like a unitary transformer. In here, we are seeing the input and output current. And now it's time to see if the control actually works. So the first test we are going to perform is just to modify this input current to, for example, 20 amperes. Also, to see the effect, I will open an analog oscilloscope. This oscilloscope is connected to the bridge voltages. So green and yellow line are the primary and secondary bridge voltages, and the orange line is the current across the inductor. So if I open the time base, you see, there is certain shift between the PWM signals. So let's increase that to 20 amperes. Sorry, 20. Yes. As you can see, currents are modifying, and also the phase shift is being modified. So currents are now in 20 and minus 20 amperes, because one is the input current and another one is the output current. That is why the difference in the signals. And the phase shift has been modified. If I move it back, for example, or interchange the sense in which the power is transmitted. So if I change that current to minus 20 amperes and click update, you can see that now we are modifying the phase shift, and now we are moving the power in the opposite direction. So let's go back and select 20 amperes. And also we can check what will happen if we modify one of the input voltages. So now we have been modifying the current, maintaining the input and output voltages constant. However, let's modify one of those voltages, specifically the input voltage. Let's modify that to 450 volts. I am just moving it in the power supply. So you can see that now voltage is going below. Yes, something like that. As you can see now, input voltage is much lower, is 450 volts. Output voltage is 500 volts. And the current that we are controlling is perfectly at 20 amperes. And the other current has been modified to accommodate the difference in voltage. So that is the use of the template, and just an example of how it can be used into a real converter.